So we stopped at seeing the exercises for analyzing algorithms after the insertion sort program. There are a few doubts I have remaining. One is we haven't seen selection sort, and the other thing is we need to consider how we modify the algorithm to have a best case running time. And the third thing is linear search algorithm, running time analysis. Okay, the next thing we need to look at is designing algorithms. We can choose from a wide range of algorithm design techniques. For insertion sort, we used an incremental approach. Having sorted the subarray A of 1 to j minus 1, we inserted the single element A of j into its proper place, yielding the sorted subarray A of j 1 to j. In this section, we examine an alternative design approach known as divide and conquer, which we shall explore in more detail in Chapter 4. We'll use divide and conquer to design a sorting algorithm whose worst case running time is much less than that of insertion sort. One advantage of divide and conquer algorithm is that their running times are often easily determined using techniques that we will see in Chapter 4. Okay, this is a new approach on designing algorithms. The design and divide and conquer approach. Many useful algorithms are recursive in structure. To solve a given problem, they call themselves recursively one or more times to deal with closely related subproblems. These algorithms typically follow a divide and conquer approach. They break down the problem into several subproblems that are similar to the original problem but similar in size, solve the subproblems recursively, and then combine these solutions to create a solution to the original problem. The divide and conquer paradigm involves three steps at each level of recursion. Divide the problem into number of small subproblems that are smaller instances of the same problem. Conquer the subproblems by solving them recursively if the subproblem sizes are small enough. However, just solve the subproblems in a straightforward manner. Combine the solutions to subproblems into the solution for the original problem. Okay, what we saw in insertion sort was a incremental approach where after solving one part you go to the next part. Here you divide the problem into such a way that each of the individual smaller subproblems are uh, are similar to the main problem itself. The merge sort algorithm closely follows the divide and conquer paradigm. Intuitively, it operates as follows. Divide the n element sequence to be sorted into two subsequences of n by 2 elements each. Sort the two subsequences recursively using merge sort. Merge the two sorted subsequences to produce the sorted answer. So they are dividing the n element array into n by 2 elements, and then they are sorting it, and then they are combining it. But my doubt here is if, for example, there are 10 elements and if you divided 5 and 5 elements each and then you sort it, but then you can't directly combine. You need to again, while merging, you need to again do it, right? You need to again sort it in order. And we also need to see how this is faster than insertion sort. That is much more simpler according to me. The recursion bottoms out when the sequence to be sorted has length 1, in which case there is no work to be done since every sequence of length 1 is already in sorted order. The key operation of the merge sort algorithm is the merging of two sorted sequences in the combined step. Okay, they have mentioned it. The key operation in the merge sort is merging of two sorted sequences. We merge by calling an auxiliary procedure merge, where A is an array and P, Q, R are indices to the array such that P is less than or equal to Q less than R. The procedure assumes that the array subarrays A of P to Q and Q plus 1 to R and are in sorted order. It merges them to form a single sorted subarray that replaces the current subarray A of P to R. Okay, our merge procedure takes time theta of n, where n equal to r minus p plus 1. So r is this value, p is this value minus 1. This n is number of elements in the array, is the total number of elements being merged, and it works as follows. Returning to our card play motif. Suppose we have two piles of cards face up on a table. Each pile is sorted with the smallest cards on the top. We wish to merge the two piles into a single sorted output pile which is to be face down on the table. Our basic step consists of choosing the smaller of the two cards on the top of the face up piles, removing it from its pile which exposes a new top card, and placing this card face down onto the output pile. We repeat this step until one input pile is empty, at which time we just take the remaining input pile and place it face down onto the output pile. Computationally, each basic step takes constant time since we are comparing just the two top cards. Since we perform at most n basic steps, merging takes theta of n time. Okay, merging takes that many times, but again, I don't know how we create those two sorted subarrays. The following pseudocode implements the above idea. Since we perform at most n basic steps, how is it that we perform n basic steps? It can't be greater than that, but it can be less. But how is it? How is that the maximum? If we have n by 2 elements in each array, the final combination merging, then we are comparing it n by 2 times, right? The following pseudocode implements the above idea but with an additional twist that avoids having to check whether either pile is empty in each basic step. We place on the bottom of each pile a sentinel card which contains a special value that we use to simplify our code. Here we use infinity as the sentinel value so that whenever a card with infinity is exposed, it cannot be a smaller card unless both piles have their sentinel cards exposed. But once that happens, all the non-sentinel cards have been placed onto the output pile. Since we know in advance that exactly r minus p plus 1 cards will be placed onto the output pile, why they are adding this plus 1 is, for example, suppose we have, let's say 10 minus 5, right? The value is 5, but then we need to count the other edge conditions 5, 6, 7, 8, 9, 10, which becomes 6, so they're adding plus 1. We can stop once we have performed that many basic steps. Okay, so they already know the output worst case running time. Merge, this is the function they mentioned earlier. It involves 17 lines where n1 is number of elements with q minus 1, q minus p plus 1, then p to q and q to r. Let l, okay, and r n plus 2 n2 plus 1 be new arrays. So for I equal to 1 to n e of p plus I minus 1. What does this mean? At the end they're adding this infinity value as a sentinel card. Okay, that is fine. For k equal to p to r, let us, this is the main heart of this algorithm. If L of I less than R of j, E of k equal to, what is k here? L of I equal to I plus 1, we are moving else A of k. What is A of k? They have not initialized the value of k. That is one thing, and the other thing is, what is this thing? What are they trying to do here? For I equal to 1 to n1, okay? Those many times they are copying A of p plus I, okay? Okay, let's see. In detail, the merge procedure works as follows. Line 1 computes the length 1 of the subarray A of P to Q, and line 2 computes the length of the subarray A Q1 to R. We create arrays L and R left and right of lengths N1 plus 1 and N2 plus 1 respectively in line 3. The extra position in each array will hold the sentinel. The for loop of lines 4 to 5 copies the subarray A to A of P to Q to L1 to N1 and for loops. Okay, lines 8 to 9 puts the sentinels at the end of the arrays L and R. This we understood. Lines 10 to 17. This is the main algorithm. Illustrated in figure 2.3 perform the R minus 1 R minus P plus 1 basic steps by maintaining the following loop invariant. At the start of each iteration of the for loop of lines 12 to 17, the subarray P to K minus 1 contains the K minus P smallest elements of. Okay, I'm lost 1 second. Let us see the figure if we will understand. The operations of lines 10 to 17 in the call merge A9, 12. My only doubt is where have they given the value of, okay, K is equal to P, this value. Okay, they are calling the merge sort A9, 12 and 16. 9 to 12 is one array. When the subarray 9 A9 to 16 contains the sequence given there. After copying and inserting sentinels, the array L contains 2, 4, 5, and 7, 2, 4, 5, and 7, and infinity. But why did the K move from? Okay, we didn't see this value. Okay, lightly shaded positions on A contain their final values, and the lightly shaded positions in L and R contains values that have to be copied back into A. Taken together, the lightly shaded positions always comprise the values originally along with the two sentinels. Heavily shaded portions in A contains values that will be copied over, and heavily shaded positions in L and R contain values that have already been copied back into A. To H. Okay, there the figure continues in the next page. Okay. A to H the arrays A, L and R and the respective indices K, J prior to each iteration of the loop of the lines. Okay. The first iteration is this, and what is the code? For K equal to P to R, if Li of K equal to, okay. So it compares 2 with 1, and since it is 1, it gets copied here. K moves to the next position in the for loop. For K to P to R, so it should move again. Again, 2 is compared with 2, right? So this 2 is copied. I moves to the next position. J doesn't move. K moves to the next position. These two are copied. Okay, let us see this. Okay, this part is okay, understood. That okay, my doubt is that this works when the subarrays are already in sorted order. So we have 2457 which is already sorted, we have 1236 which is already sorted. So when you are comparing, you can directly compare each value and put it. But for example, what if the 6 was in the first position, right? So this 245 till 245 it gets copied, then 7 is greater than 6, so 6 gets copied, then 1 comes. So what happens then? And they have not given what happens when what to do when we need to sort this uh, subarray. How do we sort the subarray? Okay, anyway. The start of each iteration of the for loop of lines 12 to 17, the subarray of p to k minus 1 contains the k minus p smallest elements of L and R in sorted order. Moreover, L and R are the smallest elements of their arrays that have not been copied back into A. What they are trying to tell us, these indices are the smallest elements prior to the next at the start of each iteration, and the elements in this are already sorted and are the smallest elements from both L and R. This is a loop invariant, which is a must, because if they are not the smallest elements from both L and R, then my doubt yeah, becomes a valid thing, because this 6, for example, if it comes here, then 1 would be somewhere in the middle, right? And it has not been copied back. We must show that this loop invariant holds prior to the first iteration of the for loops of lines 12 to 17, that each iteration of the loop maintains the invariant, and that invariant provides a useful property to show the correctness when the loop terminates. Initialization: prior to the first iteration of the loop, we have k equal to p, so that the subarray is empty. This empty subarray contains k minus p equal to 0, smallest elements of L and R, and since I equal to j equal to 1, both are the smallest elements of the arrays that have not been copied back into A. That is okay. The array indices at the termination. At this point, the subarray is sorted into two sentinels, and L and R are the only two elements in these arrays that have not been copied back into A. Okay, maintenance. What they're trying to do here is the initialization, maintenance, and termination loop invariant property. To see that each iteration maintains the loop invariant, let us first suppose that L of I is less than R of J. Then L of I is the smallest element not yet copied back into A, because A P to K minus 1 contains K minus P smallest elements. After line 14 copies L of I into A of K, the subarray of P to K will contain K minus P plus 1 smallest elements, incrementing K in the for loop update, and I re-establishes the loop invariant for the next iteration. If instead L of I is greater than R of J, then lines 16 to 17 perform the appropriate action to maintain the loop invariant. Termination: at termination, k equal to r plus 1 by loop invariant, the subarray which is a p minus p to r contains k minus p equal to r minus p plus 1 smallest elements of, and to see that merge procedure runs in data of n time where n equal to r minus p plus 1, observe that the lines Each of the lines 1 to 3 and 8 to 11 takes constant time, and the for loops of lines 4 to 7 take data of. We can now use the merge procedure as a subroutine in the merge sort algorithm. The procedure merge sort sorts the elements in subarray A of P to R. If P is greater than or equal to R, the subarray has at most one element and is therefore already sorted. Otherwise, the divide step simply computes an index queue that partitions A of P to R into two subarrays containing n by 2 elements and q plus 1 to R containing n by 2 elements. The expression x denotes the least integer greater than or equal to x and denotes the greatest integer less than or equal to x. This is the ceiling and floor. These notations are defined in chapter 3. The easiest way to verify that setting q to p plus r by 2 yields subarrays of. Okay, these brackets are what they're trying to tell. Uh, they have already examined the four cases odd, even, odd, and even to see which is it always gives this value. At this point, we'll take their word for it. Merge sort p is less than r, q equal to, okay, merge sort a of p to q and merge sort a of q plus 1 to r, and then we are merging it again. So for the first iteration, it becomes in half. This procedure gets called. No, no, no. They're calling recursively. They're calling merge sort algorithm itself. So it again goes and divides it to this it again, and the final this this would be sorted and this would be sorted to sort the entire sequence. We make the initial call where once again a of a dot length equal to n. Figure illustrates the operation of the procedure bottom up when n is a power of 2. The algorithm consists of merging pairs of one-item sequences to form sorted sequences of length 2, merging pairs of sequences of length 2 to form sorted sequences of length 4, and so on until two sequences of length n by 2 are merged to form the final sorted sequence of length n. Okay, this is the figure they are talking about, operation of merge sort on the array A. Okay, the lengths of the sorted sequences being merged increase as the algorithm progresses from bottom to top. Okay, Analyzing divide and conquer algorithms. When an algorithm contains a recursive call to itself, we can often describe its running time by a recurrence equation of or recurrence, which describes the overall running time on a problem of size and in terms of running time on smaller inputs. We can then use mathematical tools to solve the recurrence and provide bounds on the performance of the algorithm. A recurrence for the running time. How long is this chapter? Let's see. Not published the first three volumes, the art of computer programming, according to work from okay. These are the exercises. So we need to read till page 37 and we are currently in 35, okay? Recurrence for running time of a divide and conquer algorithm falls out from three steps of the basic paradigm. A recurrence for the running time of a divide and conquer algorithm falls out from three steps of basic paradigm. As before, we let Tn be the running time on a problem of size, and if the problem size is small enough, say ns less than or equal to c for some constant c, the straightforward solution takes constant time, which we write as theta of 1. Suppose that our division of the problem yields A subproblems, each of which is 1 by b, the size of original problem perform merge sort both A and B are 2, but we shall see many divide and conquer algorithms. It takes time t n by b. I'm not understanding this. To solve one subproblem of size n by b, so it takes. There are A subproblems. The time it takes for one subproblem is t of n by b, and The D often is time taken to divide into subproblems, and C often is to combine the solutions. Analysis of merge sort. Although the pseudocode for merge sort works correctly when the number of elements is not even, a recurrence-based analysis is simplified if we assume that the original problem size is a power of 2, which divides step then yields two subsequences of size exactly n by 2. In chapter 4, we shall see that this assumption does not affect the order of growth of the solution to recurrence. We reason as follows to set up the recurrence for T open. The worst case running time of merge sort on n numbers. Merge sort on just one element takes constant time. When we have n greater than one elements, we break down the running time as follows. The divide step computes the middle. It takes data of 1. Recursively solve two subproblems, each of size n. Okay, and we have already noted merge procedure takes, so it is dependent on the number of when we add the functions for merge sort analysis, we are adding a function that is, and a function, the sum is a linear function of n, that is accord adding it to. Both the time to solve and the time per array element of divide and combine steps, we can get around this problem by letting C be the larger of these times and understanding that our recurrence gives an upper bound on the running time. Both bounds are on the order. What is figure 2.5? Okay. Shows how we can solve the recurrence for convenience. We assume that n is an exact power of 2. Okay, I haven't understood the merge sort completely and the exercises they have given for, let's see, merge sort, understand in depth, and exercises of chapter 2. I think this is chapter 1 or chapter 2. For now, this chapter is completed, but I'll go back to it again. We'll start with chapter 3 later.